Hello, my dear students, and welcome back to the second part for chapter number 4 under the title of Optical Cavity for our Optical Communication course. If you remember, in the first part of this lecture, we have demonstrated together the concept of an optical cavity, where we have started with the condition to have a maximum intensity inside the cavity, which is a resonance condition. And based on this resonance condition, we have calculated together what's called the free spectral range, or the distance, the spectral distance, of course, between each two successive resonance. And then we go together with a mathematical derivations till we reach together the overall or the general form for the transmission equation, showing that by inserting R1 equal R2, where R1 and R2 are the reflection of the first and second mirror, by inserting R1 and R equals to R2, and by fulfilling the resonance condition, we can have a maximum intensity of 1. And using this maximum intensity of 1, we can conclude together that a very large electromagnetic field intensity can be induced inside the optical cavity, giving that the input is a very small value, and the beam inside, or the field inside the cavity, is given in terms of the incident beam with respect to this equation. So by inserting R2, for example, equals to 99%, then you will have 100 times greater intensity. Then we have also demonstrated together this transmission curves, showing a maximum of 1, a minimum that can be concluded from this equation by inserting this term is equals to 1. Then you can reach the T minimum condition. And this variation, where this is the resonance occurrence, is the distance between each two resonance. Let me show it here. So this one, so this distance is what's called the free spectral range, or the range between two successive resonance. As I mentioned in the previous part, the x-axis here can be either the frequency, the wavelength, of course, or can be the incremental number q. Let me also show it to you. This incremental q, which indicates the counting for the resonance occurrence that's appear here. So 0, 1, 2, 3, and so on. Okay, so this was final part we illustrated in lecture number in part number 1 for lecture number 4. In this short part, we are going just to demonstrate some properties, let me say, or some parametric view for these transmission curves in order to evaluate these curves. As you can see, there are some parameters that can affect this curve. For example, here we have the value for the reflection. The curves is given here, which is of course taken from our reference. Consider the condition where R1 equal R2. However, herein he varies the value for R. So this is 0.7, 0.8, 0.9. And by varying this R1 and R2, or these reflectance R, you can see that we have different curves with different, let me say, bandwidths or variations with respect to the resonant frequency. Also, maybe if you did not fulfill the conditions here, which is an R1 equals to R2 equals to R, or maybe if you did not fulfill the condition of resonance, you will get different data or different curves. So we need some way to evaluate the performance of these curves, or to evaluate the performance of these transmission curves. Here we are going to use maybe the same procedure we are usually using maybe in communications, which is related to the 3 dB bandwidth and the quality factor. The concept of the quality factor actually is not limited for optics, because in the RF and antenna, we also use a quality factor. The quality factor actually is a parameter that express the sharpness of the resonance. What do we mean by sharpness? Is simply this equation: the deviation of the central frequency with respect to what we call the 3 dB bandwidth, which we define here as FWHM, or full width at half maximum. So what is the full width of F maximum? It's actually very straightforward definition. Let me start to illustrate. So let's assume that our peak, that our maximum is at 1, at transmission equal 1, which is somehow this red line. So the full width at half maximum simply is implemented by getting 50% of the maximum, which is in our case will result with 0.5. Yes, here. Then we start to measure the deviation of the curve with respect to the 50%. So let me use another pen. Okay, I need this one, and then let me use another color. For example, let's use the green color. So as you can see here, for example, then we have a line here and a line here. So the deviation of the signal, or the broadening or the widening of the signal by reaching 50% of the maximum amplitude is typically what we call the full width at F maximum. So this deviation in respect to the x-axis, which is the value expressed in frequency, represents, of course, is in order to determine this delta mu graphically, you should have an x-axis of frequency, of course, because herein the x-axis is an incremental dummy variable, which is q. However, if this x-axis is frequency, then you can calculate it, or you can calculate it analytically, very simple, but by by going to this equation and by just putting t equals to 1, t equals to half. So now this is 50% of the maximum, and then as you can see, of course, k is a function of mu, so you will solve the equation in terms of mu, so you will get the mu or the delta mu at which t will result to equals to half. Here you will have two answers, simply because you have one mu to the right and one mu to the left. That's why you will get two answers, and then the difference between these two frequencies will result with the delta mu, or the full width at F maximum. It's not required to do this analytically. You can do it graphically whenever you have a transmission curves with x-axis frequency, or there is a short-term equation here. This is the substitution where with t equals to half, where results with this condition, and then when you have this equation, which is a short-term closed form equation that you can use to calculate the full width at F maximum. There is also some important note, just to avoid confusion in this part, which is the term delta mu, because we already use this term delta mu in the beginning of the lecture while describing what's called the free spectral range, if you remember. And the definition of the free spectral range, as I just illustrate, is the distance between two successive resonance. So if we go to the transmission curves here, yes, for example, this one. So let me start with the red. So the free spectral range is yes, here. Okay, so the free spectral range is this, which is the distance between each successive resonance. However, the full width that have maximum, which is let me make it with blue, for example, represents here. Yes. Oh yeah, okay, well, I will not be able to make it in a perfect manner, so I will start with some sort of reflection. Yes. Yes. Okay. So it represents the deviation here. It represents the deviation in the. It's better to make it with a smaller line. So this deviation. Yes. Okay. So it describes the deviation of the broadening of the curve with respect to the 50% of the maximum, which is half, as far as the maximum transmission is equals to 1, because again, the maximum transmission is equals to 1 if and only if R1 equals to R2 equals to R. However, for different R1, R2, or what we call an asymmetric optical cavity, the maximum will not be equals to 1. But In case the maximum is equal to 1, you will reach 50. In case the maximum is smaller than 1, then you will get 50% of the maximum, and you will determine what's called the full width at half maximum. Okay, so this is just to be sure that there is a difference between delta mu, which is the free spectral range, and delta mu, which is the full width at half maximum. Usually in the exams, in the description, I use some sort of subscript. So, for example, I told you delta mu, and then there is a subscript FWHM, which is full width at half maximum, or delta mu, free spectral range, or FSR for free spectral range. So now let's return back to the Q, which is the quality factor. The quality factor is, as I mentioned, the measure of the sharpness of the resonance. So whenever you have a sharper resonance, so for example, you can see it here that the 0.9 is the sharpest one. This will be directly reflected in the equation here, because 0.9 will have the minimum delta mu, so it will have the maximum or the highest Q. So the minimum, the broadening of the resonance, or the minimum, the free full width at half maximum, the higher the Q. Ideally speaking, this Q will tends to infinity. Whenever delta mu tends to 0, then this Q will tend to infinity. And we already have demonstrated an example, if you remember, in the atomic radiation lecture, when I hypothetically demonstrate a laser in a form of a delta Dirac function. So whenever we have a laser, which is a totally totally monochromatic light source, I can represent it in a form of something like that. So as you can see here, the free spectral range, or sorry, the full width at half maximum tends to 0. Delta mu tends to 0. That's why in this case Q will be infinity, which is of course again a hypothetical scenario, which cannot be realized in the real implementation. So this is the first parameter, which is the Q factor, and as I mentioned, it describes the sharpness of the resonance. The second factor that describes the sharpness of the or not, that also describes the property of the transmission spectrum. One of the properties of the transmission spectrum is what we call the fence. The fence is very easy, is delta mu over delta mu. We just divide the free spectral range over the full width at half maximum, and this actually demonstrates the overlapping between the broadening of the curve and the continuity of the resonance. So the free spectral range, as I just mentioned, let me do it one more again. The free spectral range is here. Yes, the free spectral range is this line, or we can make it in a straight line. It will be better. So the free spectral range is this line, is the distance between the two successive resonance in the system, in the optical cavity. On the other hand, we have another parameter, which is the full width at half maximum, which represents the deviation here. So the higher the free spectral range, which means the higher the fence, that means that you have the distance between each two resonances are far. On the other hand, this distance, this fence can also be affected if you have a very small full width at half maximum. So maybe you have two close resonance. However, the broadening of each resonance is very small, so you have a high fence. On the other hand, whenever you have a low fence, that means that either the free spectral range is small, or the broadening of each resonance is wide. That's why you have a high fence value. So this fence combine the free spectral range with the effect, the effect of the free spectral range with the effect of the full width at half maximum. And that's why it's important. Again, the ideality will go whenever the fence is equal to infinity, again, for a 0 free spectral range. Sorry, for a 0 full width at half maximum. I'm very sorry for confusion. So for a 0 for full width at half maximum. Okay, so this is the definition of the fence. Here we just substitute, because simply, if you remember, the free spectral range is given in the first slide of this lecture in this equation. So just if you divide the free spectral range over the full width at half maximum. So this will be cancelled and we'll have this on the denominator. So the reciprocal, which is this term. So this is simply the Finn's equation. Okay. This is just to remind you with the free spectral range. Okay, that's perfect. Now we will turn to another point, again related to the cavity, which is the lifetime of the photon in the cavity. What is the lifetime of the photon of the cavity? So let's now start to demonstrate the same story we have already demonstrated in part number 1, but in terms of number of photons instead of terms of an electromagnetic wave. What I mean is, in the beginning of this lecture, we have demonstrated together the trip of the light, dealing with the light as an electromagnetic wave propagating. That's why we have an E and H and direction of propagation, and we have determined together an expression for the E, the total E, either plus or minus, if you remember, and we use this in order to demonstrate the overall intensity. Now we will going to demonstrate the same story, but in terms of number of photons, because simply you have that, you know that light has a duality factor. So you can deal with light as an electromagnetic wave, and also you can deal with light as a photon, as a series of photons. So the photon is the quanta of light. So we can say that we will start the journey with NP photons. We have number of photons equals to NP. These NP photons will propagate here till it reaches the borders for the second mirror. Once this N photon will hit the second mirror, some of these photons will be transmitted outside the cavity, and a portion will be reflected back. The portion that will be reflected is defined by the reflectance, which is R2. So the amount of photons that will still be in the cavity is equals to R2 times NP. So for example, if R2 equals to 0.8, then you have 20% of the photon escape outside the cavity, and the 80% will reflect back to the cavity. Then this R2 times NP photons will travel in the back direction till they hit back the first cavity, which has a reflectivity of R1. Accordingly, some of these photons will go outside the cavity, will escape, and another portion will be reflected back. This portion will be R1. So it will be R1 times those hit the mirror. So R1 times R2 times NP. So after one round trip, you have R1 times R2 NP photons who are still in the cavity, and you have 1 minus this number, which have been escaped outside the cavity. Accordingly, we will define a very important parameter, which we call it the surviving factor, determined by S. So, I'm sorry, S, which is a surviving factor, is simply R1 times R2. So what I can say, so let me make it using the white paper or white paper. What we can say is as follows. This is the cavity. We start with 100 photons, for example, which is NB. These 100 photons travel. Some of them will escape, and another will reflect it. Those were reflected are equals to R2 times NB. So if this, for example, 100, and this is 20, this is 80%, then 80 photon will be still in the cavity, and 20 photons will escape outside the cavity. Then these photons will return back to hit the first mirror. For example, let's say that we have R1, which is again equals to 80%. So what will survive is R1 times R2 times NB, which is simply this 80% multiplied again times 0.8. So it will end with, I think, 64%. And the remaining 16 photon will escape outside. So simply you start with 100 and you end with 65. you lose only 0.64 of the input has been survived, which is R1 times R2, which we call it S, or the surviving factor. So the surviving factor represents the amount of photons that, or the percentage of photon that will be survived after completing one round trip inside the cavity. Okay, so perfect. Then if we have S percentage, which is, for example, 0.6 surviving, then we have 1 minus S escaping. Simply, if we have 64% surviving, then we have 34% escaping, which is 1 minus 0.64. So in each round trip, 1 minus S of the photons will escape, or let me say it, 1 minus S of the photons will die, because I consider that photons which escape outside the cavity are dead photon from my perspective. Again, because my main intention is to maximize the intensity in the cavity. So any escaping photon is considered as some sort of losses from my perspective. Accordingly, if I told you, please demonstrate the rate of the escaping of the photons, which is dNp by dt, how many photons you lose per unit time? So you can tell me that per round trip, I'm losing 1 minus S of the photons I have, because only S will survive. So 1 minus S will escape. In the time duration here, what's what we call the T round trip. So in the time taken for one round trip, I lose 1 minus S of the photon. Accordingly, we will define the photon lifetime Tp or tau p as tau round trip over 1 minus S, where S is a surviving factor equals to R1 times R2. So this is the photon lifetime. This photon lifetime is actually a very important parameter whenever we start our next lecture, which is the 3-level gas laser, because we will find later on that this is one of the very important adjusting parameter in a laser system. So this is the equation demonstrating the concept for the photon lifetime and how we can calculate the photon lifetime inside a cavity. Okay, let me now return back to my presentation slides. And this is the equations for the photon lifetime as we demonstrated together. Let's end this lecture with a very interesting slide. Here, this equation represents the transmission of, or the transmission inside the cavity, if you remember. And we have discussed this equation, I think, in a very detailed manner. We have discussed the condition for maximum, the condition for minimum, how this equation can be plotted, the parameter that can evaluate these equations, like the quality factor or the fence or all these stuff. But if you remember, my dear student, when we start together the journey, I told you that in order to make this life simple, I will assume that this medium, which is a medium inside the cavity between R1 and R2, is a lossless medium. I mean, whenever electromagnetic fields propagate inside this medium, only a phase change in the term of e power minus j k z is the only attributing parameter. I mean, there is no alpha, there is no attenuation, it's a lossless medium. Of course, maybe you can go home and you can resolve these equations by considering alpha. So instead of having k, you will have alpha minus j beta, and then the beta will affect the propagation phase, while alpha will make some sort of attenuation, and we will do some stuff, and you can do this stuff, and maybe we will do it actually in the next lecture, by the way. However, If you remember, okay, so I will stop a share for some seconds because I need to open another file just to make sure that you remember what I'm going to say. Because here we have to return to lecture number 3. Yeah, sorry, lecture number 3. Yeah, is atomic radiation lecture. Okay, that's perfect. Now I can go to share. Okay, perfect. So this one slide from lecture number 3. When we do together this experiment in order to investigate the effect of what's called an optical complication, optical amplification medium, if you remember. In this example, we have proven that if you have an incident light to a material and you have a detector, so this is a laser, this is a material, this is a detector. And if you satisfy this condition, that N2 is greater than G2 over G1 N1, you will have what's called a gain condition. I mean, the light getting outside the material, the detected light, will be enhanced in terms of intensity with respect to the incident light due to what's called the stimulation emission. As if you remember, we consider the spontaneous emission as some sort of noise in this experiment. The question now is, sorry, I have to, okay, let me share it again. Yes. The question now is, what if you insert this gaining medium inside the cavity? So instead of having a lossless medium inside the cavity, or even instead of having a lossy medium inside the cavity, what if you insert a gaining medium inside the cavity? Now, what will happen to your transmission equation is simply that instead of writing this transmission equation in this manner, you are going to add a gaining term to this equation, as you can see. So this G node represents the gain outcome from the amplification medium or the gaining medium you add. Okay, so it's similarly the same equation, but just we have this term G node inserted in the denominator and the denominator. So it's just multiplying the terms, multiply both terms by G node. Okay, that's fine. But now, let's see together. This is, by the way, the equation for the fluids that have maximum for the new gaining system. But this is not the issue. Now, what is the condition for maximum? Okay, let's apply the same condition. Let's apply that if R1 equals R2 and this gain condition happened, then you will get that, okay, this is very nice. You will have G node times 1 minus R square in the denominator over 1 minus G node root over 1 minus G node R square. So this is the condition. It will be G node 1 minus R square over 1 minus G node R all square. Nice. But let's see what happened if. What happened if you adjust your gain to be 1 over root R1, R2? What happened if you adjust your gain to be 1 over root 1, root R1 times R2? Okay, so let's see. Now, I just need a pen here. Okay, now this term will be 0 all the time as far as sine square kd is equals to 0, which is the condition for resonance. Okay, so this is a 0 term. We can ignore it. Now, G node equals to 1 over root R1, R2, which means that G node times this root 1 R2 will end to 1, and 1 minus 1 is equals to 0. So you have a 0 plus 0, which is a 0 in the denominator. That means that your transmission will tends to infinity. So by inserting this gaining medium and by satisfying this condition, you can reach more than one transmission, because based on the passive system or the passive optical cavity we did, we have concluded that the maximum transmission is equals to 1, which is logic. The maximum transmission is equals to 1. That means that the maximum output is equal to the maximum input. I output equal the intensity output equals the intensity input, which is logic. But now, once you add what's called a gaining system, a gaining medium with a gain G node, and if G node satisfies the condition 1 minus root R1 R2, your transmission may be equals to infinity. That means that you can insert a very small input, and you can get an infinity output. Because if you remember, transmission equals to the output intensity over the input intensity. So in order to have an infinite transmission, that means that either the output is infinity, which is something unrealistic because we don't have infinity, or the input is 0, which is the case, or which is what we can call an oscillator. To have an output without having an input. This is the concept beyond the oscillators or the oscillation. That's why lasers are light oscillation for stimulated emission of radiation, and not light amplification for stimulated emission of radiation. We will discuss this in a very detailed manner once we start our next lecture dealing with the laser theory. So this is the end for this part, and actually this is the end for this lecture number 4, optical cavity. See you in the next lecture dealing with laser theory. Thank you very much. See you later on, inshallah.